Hello, my name is AIMAN Arif bin Abdul GHAFAR and my metric number is 1181789 and my group members are Muhammad HAMIZAN bin AZMAN 1181786 and AHMAD Amin Firdaus bin SAKRI 1181790. So in this video we are going to present about Lab 1, Lab 2 and Lab 3 for subject electronic communication. So without wasting time, I'm going to start with the presentation for Lab 1, which is time division multiplexing, also called TDM. So in this lab, there are two experiments that needs to be done. So for experiment 1, we need to generate output signal waveform of triangle wave at the output port TP1 and output waveform of square wave at output port TP2 and waveform of sinusoidal wave at output port TP3. So results that we get from this experiment is shown in these three figures, where the first figures you can see the triangle waveform can be clearly seen in this picture. Is generated at TP1 without distortion by adjusting VR3 and VR1 knob. So for the second task, the square waveform is generated at TP2 without distortion by adjusting the VR1 knob. And the last task is the sinusoidal waveform, which is generated at TP3 without distortion by adjusting the VR2 knob. So to get the triangle waveform, adjust VR3 and VR1 knob, and square waveform we have to adjust VR1 knob, and the sinusoidal waveform we have to adjust the VR2 knob. So the experiment 2, we have to generate output signal at TP4, triangle waveform at CH1 channel 1, and then output signal at TDM output at channel 2. And then this next round we have to generate output signal at TP5 of square waveform at channel 1, and then output signal at TDM output at channel 2. And the last round we have to generate output signal at TP4 of sinusoidal waveform at channel 1, and also output signal at TDM output at channel 2. So the results will be like these three figures, where the first figures is the result of the task 1 and 2. We have to generate waveform at TP4, which is shown in the yellow color, and then TDM output is in the green color, where a lot of distortion, as we can see in this picture, at TDM output signal due to multiplexing in a short period. And then for the second task, the waveform generated at TP5 is in the yellow color, as you can see here, and the TDM output, which is green color, also has a lot of distortion at TDM output signal due to multiplexing in a short period. And the last task is the waveform generated at TP6 is in the green color, as you can see here, and then the yellow color is the TDM output signal. Okay, so now we move to the discussion part. We have to answer 4 questions. So first question is, describe how the multiple signals transmit on the same transmission channel. So the method that we use to transmit multiple signals on the same transmission channel is multiplexing technique, where multiplexing technique permits multiple signals to send over the same transmission channel. And multiplexing allows numerous signals to broadcast in various time slots over the same channel. And in a brief session over the channel, only one signal is allowed to send at a time. And in time division multiplexing, the overall transmission is split based on how many signals that must be sent across the chat channel. And each broadcast source is given one or more time slots in each frame for signal transmission. So the next question is, explain the method of producing the sinusoidal waveform. So to produce sinusoidal waveform, we use a Wien bridge oscillator, where a Wien bridge oscillator is one of the ways that can be used to create the sinusoidal waveform using a DC source. And the Wien bridge main component is a pair of RC networks, one of which is connected in series, while the other is connected in parallel. Op-amp is utilized to generate a gain of 3 that compensates for the RC network's attenuation. And then the R2 component is the only difference that we can see between the basic Wien bridge and the one that we use in the lab, which is the ETEK ACS 3005. And then the original wind bridge only has one resistor, but the board that we used in this lab consists of two resistors, where one is a resistor with two diodes in opposite directions linked in parallel, and the other is the variable resistor VR2 that can be changed by the VR2 knob. And then for the third question, we have to explain the method of producing the square waveform. So to produce square waveform, op-amp circuit plays the role in which to produce the square waveform. So what is op-amp circuit? You can see in this figure on the right. This is the op-amp circuit, where the charging or discharging of the capacitor depends on the RC time constant. So when Q1 is high, the inverting terminal goes below ground and the op-amp output goes high. But the RC is constant and voltage is rise. So as the voltage rising at the inverting terminal, the op-amp output then will go low. So RC time is constant and RC circuit is discharged. The op-amp circuit, there are three types of waveform that can be generated: sinusoidal, square, and triangle. So in this question, we have to produce the square waveform. So for square waveform, the rise time voltage depends on the time sequence at T2. So to produce square waveform, the positive volt and 5 volt and ground from the TDM board is connected to the power supply. So TP1 and ground from TDM board is connected to oscilloscope, and we have to adjust the VR1 knob until it produces the square waveform. So that is how we produce the square waveform. And then the last question, which is question number 4, explain the method of producing the triangle waveform. So to produce the triangle waveform, it's just the same as I said earlier, that op-amp circuit can produce three types of waveform. So to produce triangle waveform, we also use the same op-amp circuit as in the previous figure, as I shown in the previous slides. So when Q0 is high, the inverting terminal goes below ground and the op-amp output goes high. The RC meanwhile is constant and voltage is rise. And as the voltage will rise at the inverting terminal, the op-amp output then will go low. So RC time is constant and RC circuit is discharged. So for producing the triangle waveform, the rise time voltage depends on the time sequence at T1, and the connection of the TDM board with the power supply and oscilloscope is just the same as in the previous question, but this time the VR3 and VR1 knob is adjusted until it produces the triangle waveform without distortion. Before this, for the square waveform, we just adjust the VR1 knob, right? So the difference now is that we need to adjust both VR3 and VR1 knob until it produces the triangle waveform without distortion. So that is the method of producing the triangle waveform. And I think that's all for lab 1. So we can proceed to the lab 2.
Hi, my name is HAMIZAN bin AZMAN, and today I'll be present to you about lab 2 result and discussion analog to digital converter with my friends AIMAN ARIEF and AHMAD Amin Firdaus. So this lab is generally about a study of analog to digital converter using the ADC0809 device. ADC is a device that converts an analog signal such as voltage into digital form, such as binary digit that a microcontroller can read and process. So this lab objective consists of two parts, which is understanding the operation theory and characteristic of analog to digital converter ADC0809 and implementing analog to digital converter by using ADC0809 with E-Tech ACS3005 module. So we move to the result. The binary digit of experimental value of the ADC0809 single channel input begin with 0000 for 0 voltage and vary according to the analog input. voltage until it reaches 1111 for 5 volt. On the other hand, the condition of switches for each input terminal on the ADC 0809 multi-channel input are modified to produce the analog input and digital output. So the first one is the measure result of ADC 0809 single channel input. With 0.5 step size, we get 10 value of different experiment binary digit. And the second one is the measure result of ADC 0809 multi-channel input, which the switch is turned on switch 1. The first one is 5 volt, then the second one is switch 2, and the third one switch 1 and switch 2, and the fourth one is switch 3, and the fifth is the switch 3 and switch 1, and the sixth is switch 3 and switch 2. The digital input are shown in the table below. So there are two factors determine the accuracy of the digital value that capture the original analog signal. These are quantization level or bit rate and sampling rate. Bit rate or quantization give the smaller output changes in the analog signal value that result from a change in the digital representation. So then we move to the discussion. The first one is the theory of digital converter. So electronic circuit that transform the analog signal into digital signal is called analog to digital converter, which the output is binary is proportional to the input analog signal. The digital signal transport representation of real-world signals such voltage, current, temperature, and air humidity. The digital signal then is controlled, processed, and calculated. The figure shown in the slide represents the simple ADC principle. There are two main features that are important in ADC. The first one is sample rate, which is describe how fast an ADC can convert the signal from an analog to digital. Then the second one is bit resolution, which describe how much accuracy can an ADC can convert the signal from analog to digital. Then we move to the technical part of ADC. The conversion from analog signal to digital conversion can be explained from the figure. The sample block function analyzes the input analog signal at a set interval of time. The samples are taken at a constant amplitude and have a real value although they are discontinuous in time. The whole block is the second block used in ADC. The sample amplitude is only held until the next sample is obtained. Until the following sample, the whole value remains constant. This block is used to do the quantization. It transforms continuous or analog amplitude into discrete amplitude. In the whole block, the continuous amplitude value travel through the quantized block and become discrete in amplitude. Because the signal has discrete time and discrete amplitude, it is now in digital form. The encoder block translates a digital signal into binary bit form. Because digital device work on binary signal, the encoder is used to transform the digital signal into binary form. The conversion process occurs in a microsecond. Then we move to the next part, which is application of ADC. There are many applications of ADC in the real life use as it benefits to ease the human work as we dependent on digital device. Not every signal is digital, but most of them is analog. Since then, ADC is used to convert digital signal to be processed. The digital voice signal is used by cell phone. The voice is initially in analog format, which is transformed by ADC before being sent to the mobile phone transmitter. Image and movie processing, which is image recorded with a camera are saved in any digital device and converted to digital format using an ADC. Even in engineering lab, also we use ADC to display purpose and different other feature in digital oscilloscope. ADC also used in medical imaging, such as X-ray and MRI, to convert picture into digital form before alteration. They are then tweaked to make them easier to be comprehended. Temperature sensor also are built inside air conditioner to keep the space at a comfortable temperature. This temperature is translated to digital form using an ADC so that the cooling effect may be read and adjusted by the onboard controller. Then we move to the second part of the discussion, which is explain the purpose of switch 1, switch 2 and switch 3. So the main purpose of the switch 1, switch 2, switch 3 are used to control the channel selection, which we use in the second part of the result. Then we move to the next question. What are the adjustable error of ADC 0809 and explain each of them? The adjustable error of ADC 0809 is plus minus 1 LSB, same as 0.01953 volt, where the error can be divided into 3. The first one is full scale error. The full scale error is mean percent FSR between analog input and full scale analog input voltage reference in an ADC occurs when the maximum conversion value is reached. The overall error is made up of 3 types of error: full scale, zero scale and non-linearity. So the quantization error that happen invariably during digital conversion is not included in this total error. Then the offset error. The difference between the center of the least significant code and the same code on an ideal ADC with the same number of bits is known as offset error. The least significant bit LSB of the converter is used to detect offset error. The quantization interval of the converter is 1 LSB. Then we move to the non-linearity error. The non-linearity error is the biggest divergence between the calibration curve and a straight line linking the output signal to the applied force, known as the best rate. This line can be established either between the zero load signal and the normal capacity signal or another more operational value. I think that's all from me and my team. Thank you.
Hello and hi to all of my friends. Today, I would like to present to you about the lab result that we get from previous lab, which is lab 3 digital to analog converter design. My name is AHMAD Amin Firdaus bin SAKRI, and I have done the lab with my partner AIMAN ARIEF bin ABDUL and Muhammad HAMIZAN bin AZMAN. Okay, let's see the result of our lab. Before we go to the result, I want to give a simple explanation about the lab. We play around with a digital to analog converter DAC, which is a device that converts binary number 0 and 1 into a collection of continuous analog voltage. The objective of this lab is to understand the basic theory of digital analog converter, to understand the operation theory and characteristic of DAC 0800, and to generate the unipolar and bipolar analog voltage using DAC 0800. Okay, this is the first result from the experiment 1, where the state value of Vmax divided by 2 to the power of 8, we got 0.0195 volt. In the left side, where the digital input from bit 0 until bit 7, and we got V out and I out for each combination of the bits where we got the theoretical result and measured result. Okay, now this is the result from experiment 2 that we get from the bipolar voltage output of DAC 0800. The step value is 10 volt divided by 2 to the power of 8. We got 0.039 volt, and the digital output is the combination from the bit 0 until bit 7, and each of the value we measured the theoretical value and measured value, and we compare the value of V out and I out from theoretical and measured value. Okay, for the discussion, the task 1, in experiment 2, if the digital input signal is 011011010, then what is the output voltage? The output voltage for the digital input is 0.82 volt. For the theoretical value, the output is, we use the formula IREF equal to VREF over R1. We find the I out equal to VREF over R1 times D7 over 2 until D0 over 256. First, we find the IREF value. We substitute VREF with 5 volt and R1 4.7 times 10 to the power of 3. We got 1.0638 times 10 to the power of negative 3 ampere. We substitute the value IREF in the formula I out, and we get 4.4052 times 10 to the power of negative 4 ampere. To find the I out bar, we subtract IREF value with I out value, and we get 6.2328 times 10 to the power of negative 4 ampere. And lastly, we want to find V out. We subtract I out with I out bar times R4, and we get negative 0.86 volt. There is a note there. The difference between both of experimental and theoretical value is 0.04 volt due to voltage error in power supply. Okay, for the question 2, explain the resolution and step size of the DAC. 8-bit DAC that produce output of 5 volt has step size or resolution about 5 volts divided by 28. We get 19.5 millivolt. The resolution percentage of the DAC is 1 divided by 28 times 100. We got 0.39%. N-bit DAC resolution, we find it with the formula V out minus 2 to the power of n, where n is the number of bits and V out is the output voltage. Okay, for question 3, discuss the application and example of DAC in communication system and its functional operation. First, DAC was used in the audio amplifier, where DAC used to generate DC voltage using microcontroller commands. It also can be included in audio codec that include additional function in order to process signal. Second, DAC also used in the video encoder, where the process of converting a video signal into a format that can be sent. It also used to generate analog signal, digital signal, to send the number of to a number of DAC. Also, it is used to maximizing the output level of various video signal. Third, DAC also used in the data acquisition system, where the processor will pass input data to DAC for conversion to analog signal, which will be controlled by a process control N. Next, DAC also widely used in the software radio, where it is used to convert a signal of analog and send it to the mixer circuit to process before sending it to the reduced power amplifier and transmitter. Lastly, the AC also used in the digital potentiometer, where fully digital potentiometer can be constructed with some restructuring of the resistor or switch array and the addition of I2C compliant interface. The implementation of the AC in digital potentiometer make it to have output amplifier or output buffer. Okay, lastly, for the conclusion of this lab session, the experimental results slightly different with the theoretical value, which the outcome value is affected due to the equipment such digital meter and component in the module itself due to uncalibration or something else. The calibration of measuring instrument and module checking are needed before the lab is started to avoid the misleading value. Thus, the result is measured through output voltage and output current with specific situation of component where it is short-circuited and open-circuited. I think that's all from me. Thank you.